Hello everyone, welcome to Module 4, Feature Control Frame, Tolerance Zone, and TD. In this module, there are a couple of key terminologies we're going to explain, such as tolerance features, tolerance zones, TD. This diagram we have seen in the previous module. This is the key concept for us to understand geometric tolerance. In the previous module, we have explained what is datum. In this module, we try to understand the rest of it. First, what is tolerance feature? Tolerance feature means a set of geometric features on which geometrical product specifications or dimensional tolerancing is defined. That means tolerance feature is the feature to be defined use geometric specifications such as size, form, orientation, and location. You look at this drawing here, you notice there's a profile tolerance with a lead line point to the upper surface. This upper surface means tolerance the feature or the feature toleranced with this geometric tolerance or the feature to be measured based on this geometric tolerance. You look at it here, there's a bottom surface, and this bottom surface is going to be used as a datum A, and at the same time, there's a flatness here. So that means this bottom surface is the tolerance feature as well as datum feature. Why? From the flatness point of view, this bottom surface is the feature to be measured based on this flatness. Next, we are going to use this bottom surface as a datum feature in order to get datum simulator. So that's why we said the bottom surface here is the feature to be measured as well as the datum feature. Or we say it's the tolerance feature as well as the datum feature. The next important terms is tolerance zone. We have learned tolerance before. Tolerance is kind of range from the upper limit to the lower limit. Within that, the dimension is allowed to variate. Same thing from here. We have tolerance zone. Zone means there's a space. Within this space, the tolerance feature is going to be limited by this space. Usually, this space is depicted or expressed by one or two ideal lines of surface, or sometimes it's a cylinder zone. We're going to have some example here. There's a profile tolerance here. 0.4 means tolerance value. This is the value for this tolerance. This value means a zone or space with two parallel surface or two parallel perfect surface with 0.4 distance apart. There's a flat surface here. There's another flat surface here. These two surfaces is parallel to each other with 0.4 millimeters apart from each other. the tolerance feature or the actual tolerance feature supposed to be valued inside this space. We call this tolerance zone. The shape of the tolerance zone is two parallel straight planes or two parallel straight surface. Tolerance zone means as long as the tolerance feature is within this space, then this feature is meet the requirements of this geometric tolerance. Within the tolerance zone, the tolerance feature could be of any form, orientation, or location as long as it's within the tolerance zone. So you see here, there's tolerance zone, and this tolerance zone has a 0.4 distance and relate to datum A. That means the tolerance feature is allowed to have any location variation within this tolerance zone. Meanwhile, this tolerance feature can be of any orientation or the arrow of parallelism to datum A. The last one is could have any deformation or flatness arrow within the tolerance zone. This is why I said the tolerance zone means the tolerance feature are allowed to have any form, orientation, and or location arrow as long as it's within the tolerance zone. In the previous drawing, the tolerance zone is two parallel straight planes. From here, this is a position tolerance. The tolerance zone is a cylinder with the diameter 0.5. Since the shape of this tolerance zone is a cylinder, then before the tolerance value, we are supposed to have a diameter symbol here. There's a phi here. Because the shape is cylindrical. The previous example here, the tolerance zone is two straight planes. We are not supposed to put any diameter symbol here. Same thing for here. This is a position tolerance used to a hole, reference to datum A and B and C. The tolerance feature is a hole. Actually, the final tolerance feature is the axis derived from this hole. This axis is supposed to be within the tolerance zone of a cylinder with diameter 0.4. This red cylinder is the tolerance zone of this tolerance feature. So far, we have learned the tolerance zone, and also we have learned the tolerance feature. The next one we're going to learn is theoretical exact dimension, or we call this TED. Sometimes we call this basic dimension, and there could be another name, nominal dimension. The professional way is TED, theoretical exact dimension. TED only exists in the nominal model. TED can be linear TED. Here is linear or length. It could be angle. We call this angular TED. We are going to see this angular TED when we are talking about angularity. From here, TED is a length unit with a frame along this value. They always have frame here, framed value here. 25 means the value exists in the CAD model. The tolerance of this TD is derived from the geometric tolerance. TD is going to be used together with the geometric tolerance. Both of them are combined together. TD is used to define the theoretical location of this tolerance feature. Or we can say TD is used to define the tolerance zone related to datum A. Without this TD, we don't know how this tolerance zone is going to relate to datum A. TD can be used for the following purpose. Number one, define geometric tolerance. As we mentioned here, TD is going to use to define geometric tolerance. Number two, TD can be used to define the location or range of tolerance feature. Here, we have seen there's a cylindricity tolerance. And this cylindricity tolerance is not going to apply to the full length because there's a 0.57 here, the 0.77 here. That means cylindricity is only used for a portion of this path. The length is 0.57. Again, as we said, this is kind of old geometry. It's going to use inch. If it's metric, we are supposed to have 0 here. Number three, TD can be used to define the location or range of datum and datum target. In the previous one, TD is used to define the tolerance feature. And here, TD is used to define the datum or datum target. Here is the datum target symbol, A1, A2, A3. You see here, there's a shaded area. The size of the area is 5. In the upper portion, A1 means datum target. We are going to use target 1, target 2, target 3, these 3 to set up our datum. We have seen there's a TD between the datum target here. This 60 is TD only used to define the datum target. Where is this datum target is located? This TD is not used to define the geometric tolerance. It's only used to define the datum target. So who is going to use this TD? Inspector or gauge maker. Without this TD, they cannot find where those datum targets are located. They need this TD in order to find the datum target. Same thing for gauge maker. Gauge maker need this TD in order to build gauge. Because gauge need to locate parts. We are going to use the locating pin. In that case, we need TD. This TD, since it's not related to the geometric tolerance on the product join, that's why we cannot use any of this geometric tolerance to this TD. Or we said you don't have to measure this TD. It's only allow you to find where is those datum target are located at. Same thing here. When we use the TD, we should be always comparing with different specifications. TD only exists in the CAD model. That means even without specification of this TD, as long as you have CAD model, you can get this nominal value from mass data. When we put this TD on the join, it won't change anything. It won't change data. For example, here, there's a TD 15 and there's a TD 20, which is used to define the nominal or basic position of the hole to the datum or the hole between the holes. Sometimes we may notice the people we're going to specify the TD use this way. All of the TD are specified from the same original line. There's 15 and there's 35. It looks like those two ways are different because here is 15 and here's 20. Here's 15 and 35. It looks like it's different, but actually they have the same meaning. Why? Because the geometric tolerance here is position tolerance. For these two holes are going to use the same datum, A, B, C. It doesn't matter how you put this TD or even you remove this TD. The datum is still ABC. This hole, you're going to use the ABC as the datum. The same thing for here. Even you have 20 here, it doesn't mean this hole is going to use the previous hole. The datum is still ABC. So that's why I'm going to say it doesn't matter how you specify the TD. Even you don't specify any TD, the datum of tolerance feature is decided by the feature control frame here, because there's a datum here. That's why this two-way has the same meaning. There's no accumulation. The position tolerance of this hole will not accumulated to this hole. So from here, we can see when basic dimensions are used, there is no accumulation of tolerance. We have mentioned the feature control frame a couple of times. Now we're going to explain what is feature control frame. Feature control frame is a rectangle which is divided into several compartments. It contains a couple of informations such as geometric tolerance characteristic symbol, tolerance value, modifier, and the datum reference. Let's have a look at one example. This rectangle with all of the information inside, we call this feature control frame. The total, we call this feature control frame. There are just 3 compartments. The first one, yellow one, we call this symbol section or symbol compartments. It tells you which kind of geometric tolerance is going to express. Here is a position tolerance. The second compartment is tolerance zone and modifier. You're going to put tolerance zone here and some modifier here. The last compartment is datum. It's going to use to specify who is the datum and what's the datum sequence. Let's get deep inside. Here, this symbol in the first compartment, we call this geometric characteristic symbol, is a position tolerance. Next one here, this is tolerance value, it's 0.4. This means the shape of tolerance zone. From here, we know the tolerance zone is a cylinder. with the diameter 0.4 here. The next one is the multi-file. This symbol means maximum material multi-file. So we're going to learn this in the later module. The last one is the information about the datum here. Datum feature reference later. There's later here. And also we can use the material boundary symbol here. Here, there's some material multi-file. We call this material boundary. And is related to the MMB, LMB, RMB. You may remember these terms, but we're going to explain this in the later module. Here, this is the main function of this feature control frame. Feature control frame actually is kind of hub, or it's kind of center, which related all of this information together. See here? First, we know this is a profile. And then we know the tolerance value, the tolerance zone is 0.4. And then we know this tolerance zone is related to datum A. How can you relate to datum A? You're going to use this TD here, right? So this is feature control frame is kind of hub, which is related with all of this important terminology. Tolerance zone, tolerance feature, since there's a lead line here, it tells you who is the tolerance feature. And then we know who is the datum because there's datum A here, right? And then we know the tolerance zone is going to relate to datum A with TD. All right, let's have a quick review about this module. We learned a couple important terminology: tolerance feature, tolerance zone, the datum control frame, and the TD. We are going to use this important concept or terminologies again and again during the late modules. For any of late modules, you may notice we always keep asking, what is tolerance feature, what is tolerance zone, and what is datum? If you can answer those three questions, then you can understand all of this geometric tolerance. Thanks for watching. I will see you in the next module.